I guess we can get started. It's 1 o'clock here in Australia, 3 o'clock in New Zealand. I'm sorry for everyone that's attending very early in the morning elsewhere. So welcome to our session on tipping points and regime shifts in Antarctic and Southern Ocean systems. I'll introduce myself. So my name is Delphi. My research has in the past focused on ecological regime shifts and developing methods for identifying and detecting those in particularly in the Southern Ocean ecosystems. I'm currently a postdoctoral fellow at CSIRO here in Australia, working now on socio-ecological systems and forecasting future states in the context of tipping points. And our co-convener today is Nick Golledge, who's a professor of glaciology at Victoria University in Wellington. His research focuses on ice sheet modelling and detecting change over longer timescales, including tipping points. Before we begin, I'd like to acknowledge the traditional owners and First Nations peoples of all the lands that we're meeting today. For me here in Lutruwita, Tasmania, that's the Muwinina people and the Palawa people who are the current custodians. And I pay my deep respects to their elders, past and present. A few housekeeping things before we begin. So we'll have 3 talks to start with, followed by a Q&A question and answer session. And then another 4 talks and another question and answer session. There may be some time between immediately after talks for quick questions. If you have any questions for our panelists, please just pop them into the Q&A box. And we can ask them as we go if we have time. But there will be, as I said, those longer sessions. For any of the panelists so the session is being recorded. For any panelists that don't want their talk to go on to YouTube, you have until the 12th of August to notify the organising committee to remove that from the recording. I think that's all of the housekeeping. Nick, have I missed anything?
No, I think that's all good, Delphi. Thanks everyone for joining us at difficult hours of the day and night for some people. Yeah, I think we should dive straight into the first talk.
Okay, so our first speaker today is our invited speaker, Dr. Zoe Thomas. She's an ARC DECRA Research Fellow at the University of New South Wales. She has quite an interdisciplinary background, so her research is focused on understanding tipping points and feedbacks in different parts of the Earth system, including paleological and using present day data, and across systems, so ice sheets plus ecosystems, and really across a broad breadth of topics. And around determining timing, teleconnections and impacts of past atmospheric climate change. Unfortunately, she can't make it here today, but she has pre-recorded a talk, and so we're very lucky to hear from her. I think we can begin.
Michael Webber. None of this would have been possible without their support. We're currently in a climate and environmental crisis. Future abrupt shifts or tipping points in climate will have profound impacts on Earth and human systems. Examples include the irreversible melt of major ice sheets, the reorganization of atmospheric and oceanic circulation patterns, and ecosystem regime shifts. A major challenge is that there are deep uncertainties regarding the likelihood, magnitude, and timing of these shifts. Past records of climate and environmental change can help to resolve some of these uncertainties, but there are still significant data model disparities, indicating that there are major knowledge gaps. Using the principle that the past is the key to the present and future, proxy records and model simulations of past abrupt shifts can help fill some of these knowledge gaps. Headlines such as "Earth's climate monsters could be unleashed as temperatures rise," and Earth at risk of entering a hothouse climate may seem somewhat hyperbolic, but they do convey the stark realities of the future that we may face. The term tipping point was first popularised by Malcolm Gladwell in his book about social tipping points. Here he talked about how little social changes could make a big difference. This term has also been widely used to describe abrupt changes in climate, probably made most famous by Tim Lenton's paper on climate tipping elements, published in 2008, where certain subsystems were identified as being potentially vulnerable to abrupt shifts by exploring paleoclimate data. But over the last 10 years, this map has changed markedly. Here is a slightly more updated map, where we can see that many more systems have been identified as being vulnerable. Additions in the mid to high southern latitudes include the marine biological carbon pump, the vulnerability of certain East Antarctic basins, and the southern westerly winds. Recent work has also highlighted certain temperature thresholds that these systems may be vulnerable at, as well as connections between certain tipping elements through feedback effects. There are several time periods in the past that can be used to help inform on potential future tipping points. It's clear that the response of the Antarctic ice sheet to future warming will dictate the magnitude of global sea level change for millennia. But the ice sheet may be susceptible to tipping points in stability, indicating that nonlinear behaviour and rapid contributions to sea level, rather than a gradual linear rise, may be more likely. Previous time periods that were similar to or warmer than today can provide important insights. For example, the last interglacial, 125,000 years ago, had similar temperature and CO2 levels relative to pre-industrial, but a much higher sea level, indicating that there must have been substantial ice mass loss from Greenland and Antarctica. 3 million years ago, the high CO2 levels of the Pliocene can provide some analogies to a potential high CO2 future. And more recently, the abrupt ice mass loss events during the last deglaciation can also provide insights into the dynamic response of the Antarctic ice sheet. And this is something that Mike Webber will be talking about in the next presentation. At a basic level, many tipping points are characterised by a nonlinear response to a gradual forcing, and may have severe and wide-ranging impacts, and/or an irreversible shift to a new state. In some linear systems, a large forcing is needed for a large response. In some nonlinear systems, a small forcing can still elicit a large response. Certain types of systems are nonlinear but also exhibit hysteresis. This is where, if the small forcing is reversed, a system doesn't necessarily return to its previous state, and this is an example of an irreversible tipping point. On the top right, we can see here a classic example of an ecological tipping point, lake eutrophication. This is where a slowly changing nutrient content, or pH level, can quickly change a lake to being algal dominated. If anyone was watching the Rio 2016 Olympic Games, you may have seen the diving pool change from being an aqua blue to an algal green overnight, and this was a great example of a tipping point in the pool state. On longer timescales, glacial interglacial cycles are another example of a tipping point, caused by a threshold associated with a slow change in the underlying forcing. The key point here, though, is that there is no set timescale of the change, simply that it must be at a rate faster than the cause. We can depict this in a stability landscape, or a ball in a teacup kind of scenario. If we use the bottom example, our system is here in the glacial state. When the Earth gradually warms, the stability landscape will change and the ball will move over the tipping point into the interglacial state. The important point here is that there is a relationship between the resilience of a system and the shape of its basin of attraction. With a basin of attraction that is steeper and deeper, the recovery rate is fast, but a shallower basin of attraction can cause a more slow recovery rate. Here I'll show a theoretical example of a glacial interglacial tipping point. On the left here we've got the glacial state, and over time this Earth system is warming. As the tipping point to an interglacial state approaches, the basin of attraction will become shallower. This means that there is a slower recovery rate to perturbations as the tipping point approaches, and this is termed critical slowing down. Looking at the graph on the right, we can see that this critical slowing down is depicted in the pattern of fluctuations in the data prior to the tipping point. There are a range of indicators that can be used to pick up these patterns, including autocorrelation, variance, and skewness, and these are known as early warning signals. I've used these techniques on a range of systems. Here I'll briefly show an example using model simulations of Antarctic mass loss. Using model simulations of the Antarctic ice sheet under a Pliocene CO2 scenario, we looked at a number of East Antarctic basins. During the warm periods of the Pliocene, CO2 concentrations were high and surface temperatures may have been 2 to 3 degrees higher than present. Geological evidence indicates that large-scale changes in the Antarctic ice sheet occurred during the Pliocene, making it potentially vulnerable to thresholds beyond which an abrupt change in the state would occur. Here on the left we have a sea level equivalent ice mass loss for ice sheet simulations, allowing for a 0 to 2 degree air temperature bias. Here we can see that the West Antarctic ice sheet collapses quickly, but certain East Antarctic basins show a rapid retreat too. And here we can see a rapid retreat of the Wilkes Basin. In the middle we have the precursor here in grey and tipping points for a 1 degree sea surface temperature scenario, with different sliding window sizes analysing different sections of data. The black and grey lines show autocorrelation here in the top and variance here in the bottom. We can see here that both autocorrelation and variance are increasing. On the right we see showing the precursor and response in terms of thinning rate of the ice sheet. We can see here that under certain circumstances we can see a precursor indicated by early warning signals of increasing autocorrelation and variance. This analysis can really show where genuine system instabilities occur, but also can provide information on the timescale over which this instability evolves. We can see very strong indicators of increasing autocorrelation and variance found in the preceding 500 years before the collapse of the Wilkes Basin, and some weaker signals from the preceding 3,000 years. This really brings to the idea that could such early warning signals be identified in short time series of satellite era records of the modern ice sheet. Now we'll jump forwards in time to the last interglacial. 50 years ago, it was speculated that the marine-based West Antarctic ice sheet may have been vulnerable to warming and could have melted in the past. Testing this hypothesis has proved challenging, though, due to the difficulty of developing in situ records of ice sheet and environmental change spanning these warm periods. Led by Chris Turney, our team developed a blue ice record of ice sheet and environmental change from the Weddell Sea embayment, located at the periphery of the marine-based West Antarctic ice sheet. Here, the Ronne-Filchner ice shelf buttresses both the West Antarctic ice sheet and the East Antarctic ice sheet. The Patriot Hills blue ice area is close to the West Antarctic ice sheet grounding line and therefore highly sensitive to elevation changes across the broader Weddell Sea embayment. These blue ice areas are areas of ancient ice which have been brought to the surface by strong katabatic winds. When these winds blow over mountains, they remove the top layer of snow and erode the exposed ice. As the ice is removed by the wind, ancient ice is brought up towards the surface, which offers an insight into the ice sheet's history. As you travel closer to the mountains of the ice sheet, the ice that has been brought to the surface by these winds gets progressively older. This is known as a horizontal ice core, and this allows us to sample large volumes of ice from thousands of years ago, which of course usually many tens or hundreds of meters below the surface. The Patriot Hills records a hiatus through most of stage 5, as you can see here in the grey column, and this implies major ice loss of parts of the West Antarctic ice sheet. Trace gases and identification of the West Antarctic tephra B and tephra identified in Dome Fuji constrains the chronology across termination 2 in the glacial period, and places the major ice mass loss at the start of last interglacial warming. Ice sheet modelling undertaken by Nick supports this interpretation and suggests a 2-degree warming of the Southern Ocean could trigger approximately a 3-metre rise in global sea level. This data showing substantial ice mass loss early in the last interglacial indicates that Antarctica is highly vulnerable to projected increase in ocean temperatures, which may drive ice climate feedbacks that further amplify warming. Understanding the timing of these tipping points during the last interglacial is vital to understand the feedbacks between these systems. Of course, the Antarctic ice sheet isn't the only tipping element to have undergone rapid changes during the last interglacial. In a study we published in Convenors Science Reviews in 2020, we reviewed the best dated records of potential high-latitude tipping elements. These include Arctic sea ice retreat, Greenland ice sheet melt, boreal forest expansion, the Atlantic meridional overturning circulation, Antarctic bottom water reduction, West Antarctic ice loss, and Antarctic sea ice retreat. A combination of ice, terrestrial, and marine records indicate that large-scale shifts in state took place, and these were not reversible on millennial timescales. The forcings behind these changes appear to have been relatively small, implying that specific thresholds or tipping points were triggered, driving extreme, non-linear changes across the polar regions. Of course, it's not hugely surprising given the known interactions and positive feedbacks between many of these systems. With the current chronological frameworks available for these records, it's not possible to look at leads and lags on the timescales of 1 to 2 millennia or below. But what does seem clear from this synthesis is that these high-latitude tipping points all responded very early in the last interglacial. Finally, I'll leave you with a little bit of a teaser for the upcoming talk from Mike. He'll take you through this in more detail, but very briefly, this diagram here shows iceberg-rafted debris data from Iceberg Alley, and which identifies 8 retreat phases after the last glacial maximum that each destabilised the Antarctic ice sheet within a decade. The abruptness of the initiation and termination of these AID events suggests that there may be thresholds that, once passed, could trigger a destabilisation or restabilisation of the ice sheets. If these tipping points are irreversible in the sense that there is hysteresis, that is, that a direct reversal of the forcing does not allow a return to the previous state, certain early warning indicators may identify some characteristic fluctuation patterns present in the time series preceding the abrupt change. So we performed the tipping point analysis that I explained a little earlier on the Scotia Sea iceberg rafted debris stack. However, we found little evidence of robust early warning signals. This could have several reasons. I outlined some of the reasons for what we term missed alarms of critical transitions in a paper published in QSR in 2016, but there are several contenders. Firstly, critical slowing down signal could have been masked by noise. Secondly, the data resolution could have been too low, although the resolution of this dataset is unbelievably high for an ocean sediment core, so perhaps this is unlikely. Thirdly, the iceberg rafted debris may not be a direct enough proxy for the stability of the Antarctic ice sheet for this technique to really pick it up. Alternatively, of course, there could be no critical transition, in which case early warning signals would not be expected. Or that there was an early escape from the threshold, and this last point I'll discuss a bit further in the next slide. However, analysis on model simulations of these episodic phases of retreat during the deglaciation do show early warning signals. We can see here increases in autocorrelation in red and variance in purple prior to the abrupt mass loss. This here shows a schematic stability landscape for the ice sheet destabilisation and restabilisation pathways. So here the black solid lines indicate a stable equilibria and the dashed line indicates an unstable equilibrium. The small blue arrows denote the direction in which the system moves when it's not on the curve. Pathway 1, which is the destabilisation pathway, i.e. ice mass loss, and pathway 2, which is the restabilisation pathway, both show a nonlinear change associated with a critical transition. Pathway 3, which is an alternative destabilisation pathway, could indicate this idea of an early escape, with the tipping point occurring prior to the actual critical threshold. These purple shaded areas show the region in which the early warning signals would be expected. And so if the ice sheet melted along this pathway but took this early escape route due to potentially a higher noise level, critical slowing down signals might not be detected for this reason. So to wrap up and briefly summarise, understanding the timing of Antarctic tipping points is vital to inform on feedback processes. Whether systems do or should display early warning signals can help to understand the mechanisms behind some of these changes. There are interesting questions around whether there are both destabilisation and restabilisation thresholds in the Antarctic ice sheet, and whether we should really be looking for the stabilisation thresholds as an aim for us to reach. Thank you again for your attention, and please feel free to email me if you have any questions.
Okay, well, unfortunately, without Zoe being online, we're unable to take questions on that talk right now. But as she said, she is willing to answer questions by email if you do want to follow up anything with her. One thing that really sort of struck me as she was talking there is that when we think about gathering data, proxy data, if we're interested in finding evidence of rapid rates of change, threshold type behavior, tipping point behavior, it almost becomes more important to have a small interval, a short interval, a very high resolution than it does to have very long-term changes recorded. And that's something that obviously as a community we can try and target regardless of our field of interest or expertise. And I know Mike's talk coming up will probably touch on this, but it's something that can help refine a field sampling program, I think, and help target it, because in order to detect the early warning signals, as Zoe said, we need to have very, very high resolution, temporal resolution, so that we can sort of weed out what is actually a destabilizing system from what is just essentially white noise. So that's something I think we can all learn from, hopefully. Now, I'm looking at the schedule in front of me. I think we're maybe a minute or two ahead of schedule, but that's never a bad thing. Shall we move on to Mike's talk, which I believe is another pre-recorded talk, although Mike is online, and hopefully we'll be able to answer some questions in the Q&A session a little bit later on. But yeah, if we're able to jump into the next recorded talk, that would be great. Thanks.
Hello, I will talk about decay set and termination of Antarctic ice mass loss during the last deglaciation. This is basically about a paper we published a few months ago. So I wish to first thank my co-authors. Nick Golledge provided results from ice sheet model experiments, Chris Fogwell and Chris Turney data from a new horizontal ice core, and Zoe Thomas performed tipping point analysis. The study is about sediment cores from iceberg alley, shown here in orange in the upper left. The animation is from a database that tracks icebergs over the past 40 years. Icebergs calving off the Antarctic margin usually travel counterclockwise around the continent due to Coriolis force. They then merge in the Weddell Sea, they are deflected to the north and eventually melt down in Iceberg Alley, where they approach the substantially warmer waters of the Antarctic circumpolar current. Some smaller bergs may stray north and will be incorporated into the counterclockwise flow of the Antarctic circumpolar current and end up this way in Iceberg Alley. Since icebergs account for about half of the total Antarctic ice mass loss, it is important to study past iceberg shedding events to understand the mechanisms involved and to also provide better projected constraints for models of future ice mass loss and associated global mean sea level rise. What have we found so far? This is the IBRD flux rate through termination 1 in Iceberg Alley. That has been published in 2014. We found 8 phases of enhanced AIS mass loss, dubbed Antarctic Ice Sheet Discharge AID events. We also found that 3 of these AID events occurred during globally recognized meltwater pulses, with the peak of Antarctic deglaciation during meltwater pulse 1A. How does this record compare now to other studies? Here is the modeled ice mass loss from Nick Golledge for the same period. Overall, there are striking similarities between the records, at least within the dating uncertainties. There is a precursor event around 17 to 16,000 years ago, the peak of deglaciation also around meltwater pulse 1A, a decline thereafter, another peak at meltwater pulse 1B, and a final decline. So there is already a pretty firm indication that the ice mass loss at the grounding line is directly related to IBRD deposition in Iceberg Alley. How about other precisely dated archives? This is a core transect across the Ross Sea shelf. The purple bars mark stepwise ice sheet retreat events that are more or less in phase with AID events, with the largest retreat of about 200 kilometers around meltwater pulse 1B. And this is a horizontal ice core from a blue ice field in the Patriot Hills of the Weddell Sea embayment, showing 3 distinct phases of ice sheet deflation during the 3 meltwater pulses, adding up to more than a kilometer of ice elevation drawdown. So all in all, there are striking similarities between empirical records of Antarctic ice sheet retreat and modeled Antarctic ice mass loss. AID events capture, on one hand, phases of enhanced Antarctic ice mass loss, and on the other hand, phases of distinct increases in global mean sea level, primarily during meltwater pulses. Hence, there is a direct link between grounding line retreat on the continent and iceberg rafter debris deposition in Iceberg Alley. One thing we can therefore do is to estimate how much sea level equivalent ice was lost from the Antarctic ice sheet. Based on how far the iceberg rafter debris flux was elevated above the Holocene steady-state average during deglaciation, we calculated that 2.5 to 3.5 meters came from Antarctica during meltwater pulse 1A, for instance. That value is in the same ballpark as the 1 to 2.5 meters calculated by Nick Golledge based on ice sheet modeling, although it's at the upper end. Another interesting aspect is to see how long stable and unstable phases lasted during deglaciation. Based on the IBRD data, we infer that the ice sheet was stable over roughly 5,400 years, the sum of all the blue numbers, and unstable for about 5,700 years. That's the sum of all the brown numbers. So half the time stable, half the time unstable. And how long did it take to initiate and terminate an AID event? You can already see in the graph that AID events seem to have switched on and off rather than ramped up and down. Well, according to our recount, it took just a decade, or maybe a few, Those are the red and green numbers. So that's incredibly fast and scary at the same time, because this natural response seems rather independent of the state of climate, meaning regardless if it was early or late in the deglaciation, if it was cold or warm, or if sea level was low or high. Since this implies that ice sheet collapse only took a decade to fully unfold, it could mean that the current acceleration of Antarctic ice mass loss indicates another such AID event that is unfolding right now and leads to substantial ice mass loss for the coming centuries before stopping equally rapidly again. Nick Golledge used PISM ice sheet model runs that are based on satellite observations and optimized specifically to produce reliable calving and basal melt rates. The results show that decadal scale variability in Antarctic ice mass loss does occur for basal melt and calving, the top two panels, and that both reveal a one-to-one correlation with only slight leads and lags, the two bottom panels. So by extension, we can conclude that iceberg rafted debris deposition in Iceberg Alley on decadal scales reflect synchronous discharge of grounded ice from the Antarctic ice sheet. Zoe Thomas employed tipping point analysis, which shows early warning signs in the lower graphs prior to both the destabilization and restabilization for the ice sheet model data output, primarily during meltwater pulses, the orange bars at the top. And that would be path number 1 and 2 in the stability diagram on the upper right. But most AID events did not show such a clear response. It might be that this data set is either too noisy because of locally varying responses, or it may be that the system tips well before reaching the threshold, and that would be path 3 in the diagram, a so-called early escape. So at the moment, there are several possibilities here. A mechanism that can generally be invoked for destabilization and restabilization of the Antarctic ice sheet would be sea level forcing from northern hemisphere ice sheets and the response of Antarctica to this forcing, as we have published here in 2020 in Nature. Rapid ice mass loss from northern hemisphere ice sheets will lead to a regionally variable but overall significant sea level rise adjacent to the Antarctic ice margins. Those are the blue areas on the map in the upper left. Specifically in the Atlantic sector and the Antarctic Peninsula, and less in the Ross Sea. This sea level rise also causes an earlier and more dynamic retreat of the Antarctic ice sheet. Those are the curves to the right, during AID events. Depending on the pace, this forcing will be maintained for centuries and lead to Antarctic ice mass loss, specifically in the major drainage systems Ross Ice Shelf and Filchner-Ronne Ice Shelf, the yellow to red colors in the map on the lower left, until uplift restabilizes the ice sheets again. This dynamic model achieves higher Antarctic ice sheet volume at the last glacial maximum, so more sea level contribution coming from Antarctica during deglaciation. Also, only by using this interhemispheric sea level driver, the Weddell Sea embayment can actually be deglaciated to the current state, with which other models can't. So I think this interhemispheric sea level gravitational and rotational interaction is very important. So my summary and conclusions. The Antarctic ice sheet was very dynamic during the last glacial termination. Antarctic deglaciation accelerated with AID-7 event around 17,000 years ago, peaked between AID-6, meltwater pulse 1a, and AID-2, meltwater pulse 1b, and declined after 9,000 years ago. Common ice mass loss events indicate millennial scale tipping points depicted by iceberg rafted debris in Iceberg Alley, by an ice core in the Patriot Hills, by a marine core transect across the Ross Sea shelf, and by Antarctic-wide ice sheet modeling. Onset and termination of each ice mass loss event took only about a decade, and early warning signs are established for meltwater pulses, and we also see a possible sea level forcing from northern hemisphere ice sheets. As a conclusion, the recent acceleration in Antarctic ice mass loss might very well constitute a novel AID event marking the onset of a self-sustained and irreversible ice sheet retreat for centuries. Thanks a lot for your attention.
Thank you very much. That was really fascinating and very concerning as well. If you have any questions for Mike, please pop them into the chat. I think we have a couple of minutes before the next talk is scheduled. I do have a quick question, Mike, if you're happy to answer online. Otherwise, we can leave it to the end. I was really I'm not an ice sheet modeler at all, so it's outside of my expertise, but I'm really interested and concerned about those really rapid accelerations that you spoke about. And I'm wondering how well that's captured in current climate models, that sort of behavior, or if that's something that still has to be incorporated.
Well, that is actually a question you would need to ask Nick, because I'm also not an ice sheet modeler. I mean, we see this behavior, and I was struck by the consistency. You know, there are like these 8 events, and they all start the same way. They all terminate more or less the same way, and that is really, really fast. And this is a very exceptional archive where you have these very high sedimentation rate, which are not natural. They are also secondary and enhanced, but it's very unusual that you have up to 1 meter of sediment per 1,000 years. And if you do centimeter-wise investigations, you have sample resolutions that are between 5 and 10 years. This is why we can make this inference. I think this is certainly something that needs to be incorporated into the models. And I mean, with the tipping point analysis that Zoe did, that's also very fascinating. There was one aspect we haven't really mentioned. Zoe mentioned that, and I mentioned it, that for the destabilization, there are not really signs of this critical slowdown. But if we look into the restabilization, there were some signs. So restabilization, we would consider that uplift, for instance, would be the one mechanism, or the most favorable mechanism that stabilizes the ice sheet again. And she saw at least some signs in these AID events, but we don't really know. I mean, the data set could be noisy, but it doesn't really look like it because we see the sharp transition. The chronology is good enough, so the high resolution is there. Why we don't really see it in these mathematical models, I'm not really sure. Maybe Nick has to add something to that. Unfortunately, Zoe is not here, otherwise she could do it herself. Yeah, that would be my take on that.
Yeah, I can jump in. I know we're about scheduled to start my own talk, but we've got a couple of minutes probably at the end for Q&A anyway. But I mean, I would just say that you know, with all these things, you know, the models are often playing catch up with the proxy data. You know, numerical models don't like big jumps. That's part of the problem. You know, we tend to smooth things out to keep the models stable. But when it comes to things like tipping point analysis, it's stochastic variability that's really, really useful and really important. So if we're smoothing that out in the models to keep them stable, we're really throwing away a lot of the best data. Yeah. So it's not as if we can sort of put extra things into the model to capture these responses, these rapid responses. But the proxy data provide really, really important measures against which we can test whether a particular model is doing a good job and capturing the right kinds of behavior. So that's the challenge, really, and that's why sort of working together across the modeling and field teams is so important. Anyway, we should. This is probably something we can revisit in the Q&A. Let's move on to the next talk, which is me, but it's a pre-recorded talk to make things easier. So we jump into that, and then hopefully we'll have 5 to 10 minutes at the end to explore some of this in more of a discussion format. Hello, and welcome to the next talk in this session. My name's Nick Golledge, and I'm going to present some of the work that I've been doing with my collaborator, Marcus Luchak-Roche. And we're going to be looking at the velocity of the Antarctic ice sheet, and particularly trying to engage with some of the signatures of scale invariance and the evidence for self-organization in that ice sheet. So we'll start out by looking at the state of the ice sheet as we can see it today. On the left-hand side is a probably fairly familiar pattern of mass loss, familiar to many of you, I'm sure, showing the largest red circles, the areas of greatest mass loss taking place mainly around West Antarctica and the Antarctic Peninsula, some areas in East Antarctica around the Totten Glacier. And of course, that signature of mass loss can be seen most easily in surface elevation change, which is the middle panel there, just showing an area of the Antarctic Peninsula. But one thing that accompanies that elevation change is the velocity signature. So we tend to see fairly instantaneous acceleration of glaciers that have thinned in response to perhaps the loss of an ice shelf that's been holding them back, for example. So the velocity tends to respond instantaneously when the glacier terminus is exposed to a perturbation, and that draws down ice more slowly from the interior. So there's time separation there. And these two components, the velocity and the ice thickness, together make up what we refer to as the continuity equations, the equations of mass conservation. So essentially, the thickness and the velocity are convolved in the flux, the outgoing discharge from the ice sheet. And if one changes, the other tends to change as well. And of course, as the ice thins and accelerates, the outgoing flux basically leads to greater mass loss from the ice sheet overall. But the two components have quite different signatures. And what we see in the middle panel there is just a representation of a modeled ice sheet. But looking at the velocity changes that occur when you apply a perturbation at the oceanic margin. And you can see the velocity changes in discrete areas. It changes in the areas that are most fast flowing, essentially the outlet glaciers and ice streams. But in terms of mass change, what that means is that the fast flowing areas draw down ice from the interior. And on the left-hand side, you can see the map plot showing a much larger area of surface elevation change or thickness change. So we see basically a spatially diffuse signal in terms of mass change, whereas velocity change is much more localized. Now, when we're trying to understand the present day ice sheet and how much mass we're losing, it's quite hard when we're just looking at elevation change because the amount of elevation change is quite small. And of course, we have measurement uncertainties regardless of whatever tool we're using. Velocity change, because the velocities are a much higher magnitude, particularly in the outlet glaciers, it's much easier to see a change in the signal there, less uncertainty. But of course, it's a much more localized signal. So we're asking the question, is there something about the ice sheet that we can exploit so that we can look at velocity changes in a spatial sense rather than in a more localized sense? Now, one of the properties that we're exploring is the idea of scale invariance. So when we take the velocity, the surface velocity map of Antarctica, the measures data, if we plot that in log-log space in terms of the sort of magnitude versus frequency, we can see there's quite a nice power law relationship there. It forms quite a nice straight line, especially for the grounded ice. Once you get into the floating ice above a couple of thousand meters a year, on the bottom sort of right-hand side of that graph, the relationship breaks down because it's a different flow regime. But essentially, the grounded ice follows quite a nice power law fit. And this is one of the signatures of a scale invariant system. Now, scale invariance has been seen in many, many systems. It's very well known and has been for a long time. And of course, one of the most commonly understood scale invariant systems is that relating to the size and frequency of earthquakes. So the plot here on the left-hand side is showing you about the Gutenberg-Richter relationship that tells you about the frequency of earthquakes of a certain magnitude. And you can see that in each of these plots there's slightly different profiles. Some of them have inflections, others are kind of perfectly straight lines in log-log space, but they're all showing essentially the same kind of pattern. On the right-hand side, we see a similar relationship, this time something much more familiar in terms of the ice component. This is sea ice or melt ponds on sea ice, and you can see there modelled and observed maps of the sea ice melt ponds and the relationship in log-log space in the bottom right-hand side. So again, it's another scale invariant system. A lot of the work that's been done on these kind of systems is in the ecological fields. And this is one from a paper last year, looking at scale invariance of marine biomass, spanning around 25 orders of magnitude, a very clear relationship. And on the right-hand side there, you can see the pink hatched area showing you about the deviation from the straight line fit as a result of human activity. So the amount of biomass that we've taken out of the ocean that's upset this, this nicely scale invariant system. So this is a key thing with these systems, is that when we see scale invariance, it allows us to establish quite a nice baseline for what a system should look like in a statistical sense. But it also allows us to look at restructuring in that system, because if we see deviations from those straight line power law relationships, we can say that maybe the system is undergoing change, and that could be a transient reorganization, or it could actually be a more long-lived reorganization that will establish a new power law with a different gradient perhaps. Now, when we return to the ice sheets, one of the biggest changes we've seen in the fairly recent geological past, of course, is the transition from the last glacial maximum through to the present day. So this slide is showing you, again, those power law relationships of the velocity field of a modelled Antarctic ice sheet from the LGM through to present, from sort of 25,000 years ago to present day. And at both extremes, at both the LGM in the top left-hand side of those small panels and the bottom right of those small panels, the blue dots showing you the velocity data are actually pretty nicely aligned with that sort of that straight line power law. But during the deglaciation, particularly during the period sort of 15,000 through to about 13,000, the ice sheet underwent quite significant change. So I've blown up one of those panels there in the center top. That's 14,000 years ago. The modeled ice sheet, you can see that the dark blue dots are deviating from that straight blue line, showing you that the system is going through a reorganization. The velocity signature has changed, at least in the higher velocity zones. So this is a system that we know went through a change, and here is the velocity signature of that change. Now, when we look at the deviations of each of those points from the perfect straight line, we can see the residuals, and we can calculate the mean residual through time. That's what the top line graph there shows, and you can see there's very different a different regime towards the right-hand side of that than there is towards the left. The left is the LGM, the right is the Holocene towards present. And on the bottom of those line graphs, you can see the blue line, the cumulative variance of those residuals. You can see there's lots of variability through that period of transition, starting at around 14,000 years ago, peaking at around maybe 5,000 years ago, and then the amount of variability slows down. So we've gone from a system which was fairly well behaved at LGM, not very variable at all, through to one which had increasing deviations from that power law relationship, and one that then established a new mode of flowing through the Holocene. So if we return to the present day, we can actually start drilling in a little bit more closely into individual catchments. We can say, yes, there is evidence from the past that actually the flow, the statistics of the flow field do show signatures of perturbations, externally forced perturbations. What can we see in the present day catchments that might hint at those? So here we've broken down each of the catchments, and we're looking at the velocity data in each catchment, and they all show slightly different patterns. Some of them are very nice power law relationships, others show perturbations. So the question is, are those perturbations, those deviations, the inflections, are they reflecting environmental forcing,
transient or otherwise, or are they actually more related to just the different topographic or glaciological configuration of the catchments? So one way to explore that is to use simplified geometry experiments. So this is what we're doing at the moment, using circular, radially symmetric ice sheet models to look at different flow relations and different sliding laws, different flow exponents, that kind of thing, different amounts of carving. And you can see there that for each map panel, each circular ice sheet velocity field, we've got a corresponding log-log plot. And you can see that some of them form nice power law relationships. Other ones have lots of complexity to them. And what we're trying to do now is tease out what that means for our interpretation of the present day ice sheet. So this is a work in progress, but I think what we found out so far is that indeed the Antarctic ice sheet velocities do show signatures of scale invariance. And if we can understand what those relationships really mean, we can look at how the perturbations, external perturbations, might propagate into those systems. And the hope is that we can use these spatially distributed velocity fields to identify ice sheet change, perhaps even before that becomes evidence in the much more diffuse signal of mass or elevation change. So lots more work to come on this, I hope. Thank you for listening. I hope you've enjoyed it. Thank you.
Thanks, Nick. That was really, really great talk. And now we have Q&A session. So please put your questions into the Q&A box. I guess I have an immediate question for you. For looking at present day changes, what sort of time scale do you need to measure the velocity over, and at what resolution?
Yeah, it's always a thorny one, isn't it? Because it's always tempting to just say we need the highest resolution possible, both spatially and temporally. Yeah, it's tricky. I mean, it's very easy, well, relatively easy to measure velocities in a simple system if it's all flowing nice and smoothly, and we have good high quality satellite data and good markers on the ice that we can track through time. It's a lot more difficult in slow flowing areas, of course. The uncertainties get much larger. So ultimately, the way that we reduce uncertainties is to then average velocities over a certain time window. So yeah, it's a question of, I guess, cost benefit, right? You know, I think when we started looking at the deglacial model simulations, it became clear that you could see these perturbations at least at the millennial scale, and I'm pretty sure that if I dive more deeply into it, they'll be there at the centennial scale. Whether we can see that at the decadal scale in real data, in real velocity observations, would be interesting to know, and that's something that I'm keen to explore, perhaps through some collaborators in the US with some of the NASA velocity data, because they've had a program for many years gathering and processing this data in a very systematic way. So at least any uncertainties, any errors are systematic and propagate through. But yeah, it's something we're going to try and look at. And ultimately, the goal would be to try and see whether we can detect a system either becoming unstable. That would be the ultimate goal. But one thing that I'm particularly interested in is seeing if we can see an inflection in the spatial statistics, then maybe we can then track back to a time in the past and say, you know, this inflection corresponds to a change in an ocean forced perturbation maybe 100 years ago, more than that. Because generally a perturbation at the margin, at the ocean margin, will then propagate back up the glacier into the slower velocity zones. So we may see the signatures recorded there for longer time periods. But yeah, lots of work to do. So if anyone's got any great ideas, I'd like to hear them. There's a couple of questions appearing
in the chat. Should I read them out? Maybe that might be easier. So
sure.
From Thamban Maloth is asking, hi Nick, great talk. Why is the ice loss at the Ross Ice Shelf much slower than that of PIG? I don't know what that is, and Totten Glacier. although the flow is higher at Ross? Is it going to change in a future warming world?
I'm not quite sure if that question is relating to present day flow or to the models that I showed. Under the present day flow regime, the Ross ice shelf is flowing something like 1,000, well, just under 1,000 meters a year. Pine Island Glacier, Thwaites Glacier, they're flowing at several kilometers a year. But of course, they're much smaller systems, or at least their ice shelf component is much smaller, and it's much more discrete outlet glacier. They're driven much more forcibly by the oceans. There's a much greater amount of basal melt taking place in the Amundsen Sea around Pine Island, and also around the Totten Glacier. Lots of evidence of warm circumpolar deep water getting in there and driving basal melt, which leads to that localized acceleration. There's not really a whole lot of melt happening under the Ross ice shelf at the moment. But yeah, is it going to change in a future warming world? I'd say almost certainly. I think the question, at least as far as the Ross ice shelf is concerned, is whether the ocean circulation changes in a way that can essentially bring the warm water up onto the continental shelf and into the ice shelf cavity, because at the moment it's a cold cavity. But it may in future change and become a warm cavity, and in that case we're probably in trouble. Just reading through Roland's question. I saw you on the list, Roland. I knew you'd have a question. Just give me a second to read through. Yes. Yes, actually what you talk about there in terms of the grid resolution, this is actually one of the reasons that I wanted to try these Eisment experiments, because of these spokes. It's a classic experiment, a grid dependent result. But the nice thing about it is that it does allow you to then look at different flow regimes and see how things evolve. So I'm not actually too concerned about the realism of these models, in the sense that there's a lot of numerical artifacts in there. I'm actually really just interested in seeing what happens when we, for example, make n equal to 4 versus n equals to 3, or what happens if you increase sliding or don't allow sliding at all. What happens if you have just a creep dominated system? So that's kind of what that suite of experiments started to explore. And of course, there's lots more to be done in that area. But what I found so far is that actually you don't, in those radial ice sheets, you don't really get any clear power law fit if you don't have ice shelves. So if you basically have a grounded system, the ice margin obviously has to have zero velocity, so the ice speeds up as it flows away from the ice divide, but then slows down again, and you end up with very funky looking curves. So really, to get those nice power law fits, you have to have floating ice, and you have to have essentially quite rapid removal of that floating ice in order to allow the along flow acceleration. Yeah, so in terms of the specifics, model grids, geometry and resolution, off the top of my head, I can't remember, but I can certainly dig into the details and I can send it to you. But thanks for the question, very, very good.
So keep putting your questions into the question box. I guess I don't know how sensible this question is, Nick, but I'm thinking about whether you could use these changes as an early warning signal of sea level rise, jumps in sea level rise, if you think that would be possible, and over what kind of timescales do you think that could work, if it is possible?
Yeah, well, we hope it is possible. I mean, if you see a velocity change, it doesn't necessarily mean that there's going to be a sea level contribution. And that's kind of what we're hoping, is that we're going to pick up a velocity change or a change in the velocity signature at the catchment scale. that then allows you to say, you know, this is the beginning of a period of mass loss that will be manifest through drawdown from the wider catchment, which may take you know, much longer, decades to centuries. And I think that's kind of coming back to Mike's presentation. That's kind of exactly what the proxy data shows, that you can switch a system on very quickly, you know, within years to decades. But then it sort of maintains that high level of discharge for many centuries, and then finds a way to shut down again very quickly. So yeah, hopefully that's where we'll get with this, but yeah, a few steps away from that just now. Great. I think we probably need to move on. I don't see any other questions in the Q&A. There will be another Q&A at the end of this session. So feel free to keep adding questions to that Q&A box, and we can always come back to the earlier speakers if necessary. So next, we have Yingpu talking about regime shifts in central Ross ice shelf cavity. So I assume this is a live presentation. I can see you there. So we'll hand over to you. Thanks for joining us.
Thank you. And I'm going to share my screen. I guess now you can see my screen, right? Thank you. So, yes. Hi, I'm Yingpu Xiaohou. I am a second-year PhD student. I come from the University of Auckland and live in New Zealand. Today, I'm going to talk about regime shifts in Central Ross Ice Shelf cavity by comparing observational data between mid-1970s and contemporary. This project is funded by the Antarctic Science Platform. First of all, why do we care about this? The West Antarctica and the East Antarctica have different collapse thresholds, and based on Tinton 2019, the tectonic boundary between the West Antarctica and the East Antarctica sits in the middle of the Ross Ice Shelf, which makes the Ross Ice Shelf very interesting to investigate. Ice shelf basal melting can heavily affect ice sheet mass balance in the near term. Although ice shelf basal melting accounts for a large portion of ice mass loss from Antarctic ice shelves, ocean processes controlling ice shelf basal melting are seldom studied through direct measurements. The goal of this study is to look at time series of cavity hydrography observations and to identify if there has been a regime shift in Central Ross Ice Shelf since the 1970s. By talking about regime shift, I mean different water column structures and the different circulation processes. In order to achieve these goals, we decided to use observational data obtained from the G9 borehole and the HWD2 borehole. For both the boreholes, CTD profiles were deployed. CTD stands for conductivity, temperature, depth. Besides this, a hydrographic mooring was also deployed at the HWD2 location. The plot on the right is a schematic plot showing the mooring. As we can see here, the current meters and the CTD instruments were attached to the mooring. The current meter is here to detect the current direction and the current speed. The CTD instruments are to detect the conductivity, temperature, and the pressure of seawater. Salinities can be calculated based on these quantities. Here comes the results. At the very beginning, we expected there is no spatial change between the G9 borehole and the HWD2 borehole because they are both located in Central Ross Ice Shelf and there is no atmospheric influences. Besides this, they share similar depth in water column. However, if we look at the region C, we can see that a very strong process has been detected at the HWD2 borehole, whereas we can't see such a strong process at the G9 borehole. We attributed this to spatial regime difference. And in order to explain this, we introduced the local basal variations to the ice shelf roughness. If we shift our focus to the region D, we can say that the meltwater covers a wide range in salinity, whereas there is no such signal at the G9 borehole. Now let's move on to look at the mooring data. The mooring data tells a similar story for meltwater. The meltwater covers a wide range in salinity, whereas the temperature clustered at around the in-situ freezing point. If we look at the temperature salinity diagrams in different months, we can say that in January and July, the meltwater usually has a relatively high salinity, whereas in October, the meltwater is relatively low in salinity. In order to explain this, we introduced the progressive vector diagram, which I will talk about later. And because of the change in salinity, the meltwater has a seasonal cycle. Then if we look at the mid column, we can say that the extremes of temperature happened at the mid column, which cannot be obtained by mixing with upper or below water masses that has intermediate temperatures. The guiding line here shows that the mid column has a strong process all year round. Again, we look at the temperature salinity diagrams in different months, and we realized that in July, the temperatures at the mid column can seldom go below the surface freezing point. This can be explained by either short-term oceanic processes, such as eddies, or long-term ocean processes, such as seasonal cycles. Lastly, we look at the deepest region. The deepest region deviates from the rest, which indicates a new circulation pathway. We tend to believe that this has happened because of the high salinity shelf water penetrating into the cavity through mode 1 circulation. Here comes the progressive vector diagrams. Progressive vector diagrams are produced by integrating currents. If we look at the 3 different months for the uppermost layer, we can say that for January and July, the progressive vector diagram shows a northward direction, whereas for October, the progressive vector diagram shows a eastward current. Therefore, we concluded that meltwater with different salinities can come into the cavity because of the currents. We also compared progressive vector diagrams in different depths, and we realized that the most distinctive one is the uppermost layer. Lastly, we tried to select eddies from the progressive vector diagram. In order to do that, we introduced a principal selection requirement called current direction. If we look at the plot on the lower left, we can see that when an eddy comes and passes a fixed location in central Ross Ice Shelf, like the HWD2 site, it will always cause the current direction to change at 180 degrees. After introducing this principal selection requirement, we got some eddy candidates. If we look at the plot on the right, the selected eddy candidates shows that most eddies need 10 days or even less in order to pass the HWD2 site. Because we are very interested in understanding how the meltwater salinity can be affected by the currents, we plot out the progressive vector diagram together with the wavelet analysis for salinity. Generally speaking, when the salinity is relatively high, the progressive vector diagram shows a westward current. When the salinity is relatively low, the progressive vector diagram shows eastward currents. We also realized that when the salinity is relatively low, the wavelet analysis shows a strong variation in salinity. This can be explained by 2 assumptions. The assumption 1 is related to the meltwater salinity. When meltwater with relatively low salinity comes into the cavity, it can cause salinity change, which can then drive variations. Another assumption is related to currents. When eastward currents flow, it can drive variability because of the seabed topography. Therefore, the variations obtained here may be attributed to eastward currents. Here comes the take-home messages. First of all, the hydrographic data from the Central Rosyth Shelf indicates that the currents do affect meltwater salinity. Secondly, based on our preliminary analysis for eddies, we suggest eddies mostly need 10 days or even less in order to pass a fixed location in Central Rosyth Shelf. Lastly, after comparing the observational data from the G9 borehole and the HWD2 borehole, we do see differences in spatial aspect. I would like to thank Antarctic Science Platform for the funding, and I would like to thank my supervisors for their great support. That is the end of the talk. Thank you. I will stop sharing.
Thank you, Ying-Pu. We're a little bit behind time, so we might move straight to the next talk, but please pop your questions for Ying-Pu into the chat and we'll get to them in the next Q&A session. So now we'll move to the next speaker, who is Graham Rickard, who's speaking again about the Ross Sea, but now looking at CMIP5 and CMIP6 models. So Graham, the floor is yours.
Yeah, I don't see Graham on the participant list. Is somebody else presenting his talk? I don't think he's submitted a pre-recorded talk, has he? Right, it seems that Graham is AWOL and there's no pre-recorded talk. Which is a shame. I was looking forward to that. Maybe we just jump straight on to the next talk. And I can see that there are some other NIWA people in the audience. I'm thinking of you, Craig Stevens. If you know where Graham is and you can prompt him to join our session, maybe he can give his talk at the end. Right now, though, we have Vanessa Teska talking about warm deep water intrusions in Filchner Trough.
Yes, well, good morning from Europe. Let's see. No, yes, thank you for the introduction. I will talk about warm deep water intrusions in the Filchner Trough and the Weddell Sea in CMIP6 simulations that were performed with the RV climate model. Oops. And in recent years, so last 20 to 30 years, observations from cruisings and moorings have shown that intrusions of modified warm deep water origin from the Weddell Gyre are intruding into the Filchner Trough and onto the shelf east of the Filchner Trough. Those intrusions mostly occur in summer and autumn and then reduce in strength or vanish completely during winter. And interestingly, they could also reproduce in numerical simulations, like this example here on the right side with Brios and the HCM3 scenario. And those simulations showed that these intrusions may become stronger in the future, may become longer lasting, and might even switch the Filchner Trough into a warm state where it's completely filled with this modified warm deep water, and then it allows it to intrude into the Fechner cavity, thus increasing basal melt rates and enhancing the flow of grounded ice there. We looked at the scenario simulations performed with the RV climate model that consists of a finite element sea ice ocean model FESM and the atmospheric part Econ 6. And we looked basically around 100 years. So it covers the time from 2015 to 2100 with the scenario simulations. And to have an impression for recent climate in this model, we also took the last 15 years of the historical DEC simulations, so 2000 to 2014. And we were quite surprised actually how good this model result is, because temperature, the bottom temperature for the southern Weddell Sea continental shelf, here the look towards the south, in the surroundings of the Fechner Trough are actually quite near to observational data. So the largest differences can be found east of the Fechner Trough and just at the sill. And that's exactly those areas where we have variable intrusions of warm deep water. So we're looking here at a 15-year average, and still we are quite near to observations, and that is quite good for a climate model, ocean model, we have to say. The same is true also for seasonal salinity data. Now, how does this develop towards the end of the century? When we look at the difference between the last 15-year average and the start of the century, so 86 to 2100, to the average of 2000 to 2014, we find that the Fechner Trough will warm drastically by at least 2 degrees Celsius. And it will, in the lower layers, also get saltier. Now, this is one state, this is the other state. How does this develop? And in general, the average temperature in the Fechner Trough already starts to rise in the next 15 to 20 years. So between 2030 and 2040, especially in the high forcing scenarios, so the 8.5 or 7.0, in this figure is the 7.0 scenario, sorry, temperature will already start to rise here and reach this 2 degrees Celsius difference or more to the state it is now in. But studies and observations performed previously have shown that there are few factors that influence this temperature rise. And that is, for one, the sea ice formation on the continental shelf especially, and the depth of the Antarctic slope front. Sea ice formation in this figure is shown in blue, in hues of blue, and the depth of the ASF is in black. And we wanted to know which area actually has the bigger influence. So the sea ice formation in Fechner Trough directly, or the sea ice formation upstream that is then transported downstream and does what it does. So let's take a look at all those components. The slope current, so that the current that lies below the ASF and also transports the warm deep water, shows a continuous warming throughout all climate scenarios, independent of the forcing. So this is quite interesting, but probably not what we're looking for. Then the thermocline, as I already said, might influence this. And here it gets interesting because the thermocline actually rises in depth. So more than 150 meters in the higher forcing scenarios, so 7.0 or 8.5. And less so, but still visible in the mitigation scenarios, 2.6 or 4.5. Then sea ice formation on the shelf, so this means in Fechner Trough, decreases in the high high emission scenarios. This is the dark, thick blue line, but doesn't do that the same in the 2.6 scenario. So there we see a difference additional to the depth of the thermocline or the ASF. And in contrast to the happenings on the continental shelf, upstream sea ice formation actually reduces continuously or nearly continuously down to nearly nothing in all climate scenarios. So there's not that much of a difference. So we have those factors, and we know that the temperature in the Fechner Trough rises quite early, starts to rise quite early. But that's not the only thing going on there, because observations showed seasonal variation in this warm inflow, and we found that as well as longer lasting pulses. So we have phases actually of warm inflow and colder phases that last 1 year, 2 years, sometimes multiple years in the future. And this longer lasting pulses actually increase in their frequency and duration, starting from the 40s in, well, all scenarios we looked at. But only in the first two scenarios, so the top 2, 2.6 and 4.5, does the Fechner Trough actually always return to its cold state. In the other scenario, the 7.0, which we have 4 ensemble members here, and the 8.5, these increased inflows lead to tipping into a warm state. So the Fechner Trough is suddenly not filled with ice shelf water anymore, but instead is filled with modified warm deep water from the Weddell Gyre. And this, of course, has far-reaching consequences for the Fechner ice shelf, for melting rates, and so on. Now, that was only looking at the yearly average temperature, but if we take a look at the seasonal variations, we also see the influence of the increased inflow. In the bottom plot here is the 8.5 scenario and the seasonal variation, basically. So the larger the bar in the plot, the larger the difference between the larger the maximum temperature difference in the Fechner Trough. So maximum temperature, the red dots, show basically when there's maximum or the value of the maximum inflow, and the blue dots are the minimum. And as you see in the late 50s or early 50s, and later on in the 8.5 scenario, this span reduces drastically. So as soon as there are more frequent, longer lasting warm water pulses entering the Fechner Trough, the seasonal signal gets lost. And here let's come back to the sea ice formation, because as you see, the sea ice formation actually shows a strong relation to the seasonal signal. As soon as the sea ice formation reduces strongly over several years, the seasonal signal also gets lost. And that is not visible in the 2.6 scenario. That will not tip towards the end of the century. So let's recap. In the 2030s, we see already the rise of temperature starting. Then beginning of 2050s, the frequency and duration of this warm water pulses increase, starting to develop a correlation between sea ice formation on the Fechner Trough and the seasonality. And in 2075, in most scenarios, the stronger scenarios, the Fechner Trough has tipped. Now, when we put all this together, we come to the conclusion that this is for a combination of the lift up of the thermocline and the sea ice formation. So as soon as the ASF is high enough above the sill, water can enter easily into the trough, and then the sea ice formation develops its influence onto these warm water fluxes. Thank you.
Very nice,
Thank
Vanessa.
you.
Thanks,
Yes.
thanks for that. And actually touched very nicely on the conversation we had in the Q&A about the Ross cavity and when that might switch to a warm mode. So that was a really nice counterpart to that discussion. I'm a bit befuddled by the timing now because of the switch around, but yeah, I get the sense maybe we could probably do questions now if people have them, or we can save them up for the Q&A. If anyone has any burning questions, pop them in the Q&A. It's quite confusing having a Q&A box and a Q&A part to the session, but I think you all know what I mean. Okay, I'm not seeing any questions coming in or any hands up or anything, so shall we just move along? And next up, we've got Clara Azarian, current and projected patterns of warming and marine heat waves in the Southern Indian Ocean. Something of relevance to many of us, I think.
Can you hear me?
Yes, we can hear you.
And can you see my screen?
We can see your file browser, yep.
Thank you. So hello everyone. My name is Clara Azarian and I'm a first-year PhD candidate, and I'm going to present this work on current and projected patterns of warming and marine heat waves in the Southern Indian Ocean. And I would like to thank the co-authors for their contributions and mention that the content presented here is included in the paper that is to be submitted soon. So let's start. We focus here on the Southern Indian Ocean because first, it is one of the regions of the world where most of the recent ocean surface heat gain has been concentrated in recent decades. And secondly, because it hosts a rich biodiversity. And indeed, it covers important fisheries, but also petromineral species, with, for instance, among the largest populations of megafauna in the world. And so to protect that biodiversity, there are conservation measures that are implemented, but they do not take into account climate change yet. And although there are fisheries, they are not as putting as strong pressure as in other parts of the world. And so as we expect an important climate change signal, climate change may become a major threat to ecosystems, and this region could be considered a natural laboratory to study that. But in order to study climate change impacts on biodiversity, we need to be careful about the scales. And climate change is often studied through large-scale processes, whereas ecosystems are mostly driven by finer-scale processes, or you could say an oceanographic meteorology. And although we have information on warming rates in the Southern Ocean at the Southern Ocean scale, this information is still too coarse-grained to be useful for policymakers. And that's why we need to focus on scales that would be relevant for conservation. Here in the study, we particularly focus on temperature, trends, and extremes because temperature is an important driver of species distribution in the region. And so we can consider that the temperature trends and extremes will be important potential drivers of change, or we could say climatic impact drivers to take the IPCC concepts. And so our aim here is to regionalize temperature-related climate impact drivers. First, trying to see if there are robust trends in the observations, then focus on regional projected patterns and see how all of this could be useful then for conservation. For that purpose, we use observations and synaptics models. We focused on two shared socioeconomic pathways, or SSP, SSP 126, under which we meet Paris Agreement goals, and SSP 245, under which we don't, but it's a likely scenario given current policies. In terms of metrics, we use the warming rates, but also climate velocities as defined on the right. And climate velocities can be interpreted as the speed an individual should have to remain at the same temperature. We also focus on marine heat waves as defined by Update et al. 2016. So that is using a climatology and a threshold estimated for each grid point and for each day of the year using an 11-day window. And we consider that we detect a marine heat wave when the temperature is above the threshold for at least 5 days. So it's a statistical definition. So now for the results. So here you have a map of the warming rates calculated with observations over a 40-year period. And you can see the important spatial heterogeneity. You also have on the left the time series for some specific areas. And you can see in orange the important variability west of the Kerguelen Plateau. And when we compare warming rates between observations and a 24 model ensemble, you see that although the mean warming rate is consistent between the two datasets, the spatial patterns and the variability is not very well reproduced by the model ensemble. And so we can wonder whether this variability will then impact the projections. If we can, for that, focus on one particular model from the IPSL and look at different members that are simulations with different initial conditions. And you can see on the left that over the historical period, you have a diversity in patterns of warming rates between the members. But then as we go through time under SSP 245 on the right, and we look at the similarity between the patterns of change between the members relative to 1, we see increasing similarity. And this would suggest that anthropogenic forcing might become more dominant in determining the spatial patterns of change compared to natural variability, and so that the projections could still provide useful information. So now let's look at the projections. Here you have the surface temperature change relative to 1995-2014 for both scenarios and under different future periods. And you can see on the both scenarios, the latitudinal patterns of change, but also this intensification over the subantarctic region between 40 and 55 degrees south. And then if we focus on SSP 245 and we add information on the metrics about marine heat waves intensity and the mean number of days affected by per year affected by marine heat wave for different time periods, you can see again in the long term this intensification over the subantarctic, and especially over Crozet and Kerguelen Plateau. You can see that in the long term we may almost reach a permanent state of marine heat waves, so that may have important ecosystem consequences. We also find with the climate velocities that at the end of the century they are faster in the mesopelagic, so between 200 and 1,000 meters compared to the surface between 0 and 200 meters under both scenarios. And in some areas, it can be up to 10 times faster. So this could have also important ecological consequences for species that are relying on the whole water column, either for foraging, but also throughout their life cycles, like for the Patagonian toothfish, for instance. This also means that if we only focus on surface conditions to estimate distribution shifts, we might actually underestimate them because there is this shift between what happens at depth. So here is a summary of the regionalization we can do based on the different metrics. And you can see that the boundaries reminds of some dynamical feature, notably highlighting the important role of the Antarctic circumpolar current for the patterns of change. We can also point out the overlap between intense climatic impact drivers and important ecological areas in the subantarctic in the zone 3. And even more so given that we could have changes of surface temperature of more than 1 degree, even under an optimistic scenario. So this shows that it should be of interest for conservation, but also with the thinking about adaptation as well. It is important to further make the link between physical indicators and potential consequences for ecosystems. And here we can look at climate velocities in the context of biogeochemical provinces as defined in Regondo et al. 2020. And each province corresponds to a unique regional environment that shapes biodiversity. The color map here corresponds to today's conditions. And as a first approach only for temperature, we can simply shift the exclusive economic zones boundaries, distinguishing between surface and mesopelagic. And for instance, here, for example, in Amsterdam, you can see that in white already today, it's overlapping 2 provinces. But in the long term, for the mesopelagic conditions, which are in bright pink, it may evolve towards conditions observed today in the South Subtropical Gyre province, while the surface conditions in bright blue will mostly be under south subtropical convergence conditions and almost no longer under subantarctic ones. And again, it's only for the temperature aspect. But this shift between surface and mesopelagic could have major consequences if we're in transition zones such as this. So to summarize, there are increasing concern in the literature about warming and marine heat waves being threats to ecosystems, but today we still lack adapted indicators to evaluate the risk posed by climate change at scales that would be relevant for conservation. And so here, this is a case study on the Southern Indian Ocean to regionalize potential impact drivers using observation and semiptics models. We showed that current patterns are spatially heterogeneous and dominated by natural variability, but we still can learn useful information from the projection, and especially this intensification over the subantarctic, which can be associated with a positive feedback loop with the ACC dynamics, and also that there is this difference in the projected climate velocities between the paces of change between the surface and the mesopelagic. In terms of perspective, I've also studied marine heat waves at depth using observation, and if I have time, I'd be happy also to talk about it if it is of interest. I would also like to mention that we could also look at the reversibility of the change, since we are in tipping point session, using overshoot simulations that are available on the SEMIP6. That would be interesting to see because there are some preliminary results showing that in the Southern Ocean, there might be some irreversible change as far as temperature is concerned. And last but not least, I think that a main step forward would be to further make the link with ecological thresholds and in terms of order of magnitudes of the changes, and see in a cross-disciplinary manner which indicators of change would be relevant for policymakers and how they could be actually triggers for action. And I thank you for your attention.
That was awesome, Clara. Thank you very much. That was a very interesting and thought-provoking talk, somewhat alarming. One thing that sort of sprung to mind, I'm not an oceanographer, of course, but I'm just thinking, you talked about permanent heat waves, and of course, I know what you mean, but it's inherently an oxymoron, right? So if we move to this warmer state, then there will be heat waves within that warmer state, right? So that's even more alarming, right? What are the extremes of the new extreme state? Do you have numbers on that? I mean,
yeah, it's true. Already, it's true that it depends of what we define as marine heat waves and what we're trying to show actually. So when we define marine heat waves, we use this baseline, this climatology, and it's true that from what I've shown is still based on the baseline from the historical period, because that's what we consider to be the living conditions for the ecosystems. And so the interpretation will then be that the permanent state of marine heat wave is those ecosystems will be under extreme conditions all the time relative to what their living conditions today is, if it makes sense. But then so I didn't look at using another threshold, but what I can say is that most of the increase in marine heat wave that we see using this historical threshold is due to also the warming, because we're shifting the distribution of temperature, and this is mostly that rather than an increase in the variability and variation. There is some increase, but it's mostly driven by the mean warming.
Excellent, thanks for that. Anyone else want to jump in with some questions? Delphi.
Yeah, I'll jump in. Great talk, Clara, really interesting, and special interest for me in that region. I'm really interested in this, what you were saying about the difference in the velocities between the surface and the mesopelagic, and what the different mechanisms for that are. I was wondering if you could expand a little bit on that. It's really interesting.
Yeah, I think it's mostly because when you define the climate velocity, so it's the ratio between the warming and then the spatial gradient. So it doesn't mean that the mesopelagic is necessarily warming more, but it means that in terms of isotherms, because the gradient in the mesopelagic is smaller compared to this at the surface, then it means that you would have to travel further to stay at the same temperature. So it's mostly another way to look at the speed of change in a way that would be more relevant for ecosystems.
Yeah, that's really interesting for all those fisheries, which are really deep water fisheries and moving fish stocks. Yeah, really fascinating. Are there any other questions? Please keep popping them into the question. So questions for Clara or for Vanessa or Ying Pu, please add them in. We're having trouble contacting Graham, so I'm not sure that he's going to join us, but please continue to add in questions for any of those talks. I think you can also raise your hand if you want to ask a question in person.
I see one raised hand there from Tamban Naloth. Let me see. Yep, I think you should be able to speak.
You can speak.
Yeah, can you hear me now?
Yes.
Yeah, Clara, excellent talk. So I was just wondering actually, so now since you talk about the marine heat waves increasing actually as we see today, in fact, including the Northern Indian Ocean also is warming quite a big way, which is also influencing a lot of climatic things out there. So my question is that actually that as the marine heat waves are increasing, so would be the more increased freshwater melt contribution, like for example, melting of sea ice and other available ice around Antarctica could also lead to some stratifications. So the upper layer could be more what you call lighter, and therefore they could be more stratified. How would this be impact your ecosystem in kind of thing what you're talking about?
So if I understand the question correctly, you mean like how would this stratification would impact the ecosystem as well, or?
Yes.
Yeah. Well, it's a bit out of the scope of the study I've done, but maybe an answer would be that we have an intern that has looked at the phytoplankton outputs in CEMIP6. And actually, so because the primary productivity in the region is constrained by nutrients and light, and so the stratification can have an ambiguous impact, because it can either prevent this input of nutrients from below, but it can also increase the exposure of the phytoplankton to light. So depending on the latitudes, it can actually, the stratification can actually increase the productivity. And that's what we see in some simulation, is that we have this increase in phytoplankton productivity, because we have this increased stratification that is overcoming this constraint of light exposure. But then in terms of the mixed layer, there is a difference actually between CEMIP5 and CEMIP6 simulation over the subantarctic, because there are different representation of the winds. The westerlies are intensifying with climate change. So it could also have this effect of deepening. As they are not represented in the same way on the CEMIP5 or CEMIP6, there are slight differences depending on the models. So the increase in primary productivity can also be modulated by that. And then with productivity, we'll have the rest of the ecosystems that may rely on that through bottom-up effects. So I hope it answered the question. I'm not sure.
Yeah,
if that was,
thanks.
Yeah.
You're clear at the moment.
We have another question from Will Hobbs, who's asking you, Clara, again, that just questioning when you said that you don't have indicators of change. Is that because we don't understand the important indicators for ecosystems? That's intensity, duration, threshold temperatures, for example. or because physical models don't yet capture those mesoscale processes sufficiently?
Yeah, so it's a bit of both, because there is this, I mean, it would mean that for ecosystems, we need to choose whether for one species we say, well, its thermal tolerance is such temperature, or so it would be species specific, and so it requires some intense work on that. Then in terms of ecosystem, it's a bit more complicated to really know what would be the trigger, so it will require further research. But the point that you make on mesoscale processes is really interesting. It's a bit of the core of my PhD. It's actually to really see what would be the impact of climate change on the mesoscale processes, which are, as I said, actually driving the ecosystem. So there is also a bit of that that remains unknown, and that can be a limitation today in terms of indicators.
And another more of a comment from Roland, following on from Nick's comments before about these kind of shifting baselines in what's a normal temperature. He's saying it might be interesting to explore future extremes with a shifting heat wave baseline to see whether future heat waves would be more extreme excursion from the mean than today's.
Yeah, for sure. And maybe just to add up, it's just a thought that I'd like to share, since we may have a bit time. It's that's the marine heat wave. When I looked at the marine heat wave at depth, we could start to see maybe also a relation between marine heat waves occurring and the polar front variability and meanders, because when the polar front meander, it can be an incursion of warmer water southward, and so making also the link between the heat waves and this type of feature that is important for ecosystem is important. And I think as Roland said, I think I'll also look at those, see if there's more important variations, because it could also be related to increased variability in the polar front.
Interesting. So are there any other questions for Clara or for Yingpu or Vanessa? I guess I have one maybe for you, Nick, about how these kind of findings can be incorporated into ice sheet models and developments at the oceanographic tipping points that we're identifying.
Yeah, no, it's an interesting area, and one thing I've been interested in over quite a few years now, almost a decade, is the role of ice sheet meltwater from the ice sheet, from the Antarctic ice sheet, changing the oceanic conditions in the Southern Ocean at high and mid latitudes. So one thing we're looking at the moment, actually, we have a project exploring the role of future ice melt in terms of changing ocean temperatures in the low latitudes, tropical Pacific particularly, thinking about viability of coral reef systems. Can the ice sheet melt save the corals? There's a headline for you. So we've got some work to do on that. We've been running a lot of global climate model simulations to look into that, but it's more tricky than it should be. So yeah, lots of work to do around there. But yeah, I'd like to think that there's a lot of areas where we overlap between the physical and ecological sciences, and we should be talking a lot more. That's why I think this session hopefully has been stimulating for all participants. I've certainly learned a lot, and it's been great to sort of see these ideas coming together. Now, there was just one last question came up in the Q&A box just as we were talking. Another one for Clara, I'm afraid. Does the heat wave affect the lower benthic area also?
Yeah, so it could. It's true that what I've shown here is mostly marine heat waves detected at the surface. So the thing is, for marine heat wave detection for now, we need daily data, and we don't have it for simulations at depth. So it's hard to say that in terms of order of magnitude, but then yeah, there is no reason why they couldn't be heat waves at depth also.
Great. I am tempted to wrap things up a little ahead of schedule, unless anyone else got more questions, comments, or just wants to say hi. We do have a few minutes before the formal end of the session, but I can see a few attendees sort of dropping off. But yeah, I just want to take this opportunity to thank everybody for participating. These online conferences are as good as they can be given the circumstances. You know, I think there's a lot of hard work goes in to setting these things up. So I want to thank our IT support for navigating us through this session. Tempted to say without glitch, but we did have one lost speaker, so that's not an IT glitch, but a little bit of a setback. But yeah, it's great that everyone can participate. I know it's been difficult times for some people, but we've all managed to get together, and that's the main thing. Delphi, is there anything else you want to add?
No, I just wanted to say I agree with your comments. It's been a really interesting question, and I think, yeah, the next kind of part is, as you say, Nick, fitting all of this together into a bigger picture of how the ice sheets, ocean ecosystems all work together, and how those kind of tipping points can cascade through. It's really fascinating future research ahead. I'd also like to thank all of the participants. Yeah, it's been fascinating.
Great. So keep up the good work. Thanks for participating. Enjoy the rest of SCAR, and hopefully we'll see each other in real life one day soon. Thanks, everyone.
Presentation.
Shall I end the session?
Thank you.
Yes, please. Well, that's end of the session there. Thanks.